In this video, we discuss binomial heap. We discussed before what a binary heap is. So binary heap is represented by a complete binary tree satisfying the heap property. It could be a min heap or max heap. For min heap, the smallest element is at the root. For a max heap, the largest element is at the root. For such a heap, finding the smallest element is of big O time complexity. And if it is a max heap, that means finding the largest element. And the time complexity for inserting a new item into the heap is big O log n. And deleting an item, it is big O log n also. And merging two heaps, the time complexity is big O n. For a binomial heap, it has the same time complexities for finding, inserting, or deleting. But for merging, it is more efficient. It is of time complexity big O log n instead of big O n. To understand what a binomial heap is, we have to first understand binomial tree. We can define a binomial tree recursively, as shown in these two diagrams. So this is an order 0 binomial tree, or B0. It only has one node, the root. For order 1 binomial tree, or B1, it has a root and a child, which is the root of B0. And then B2, it has two children. This is B0, B1. And for order 3 binomial tree, B3, it has a root, and then the three children, B0, B1, B2, and so on. So this is B4, root, B0, B1, B2, B3, so totally 4 children. So it is defined recursively like this. The ith binomial tree Bi, I is larger than or equal to 0, like B2, consists of a root and I children, like B2 has a root and 3 children, B3, 1, 2, 3. Where the ith child, j equals 1 to up to I, so we call this first, second, third, is in turn the root of a binomial tree Bj I minus 1. So the first one, so that means this is B0, the root of B0. This is the root of B1. It is the root of B3. So it is defined recursively. And Bi can be decomposed to 2 Bi minus 1. Like this one, this is B2. So we have this B1 and B1. So 2B1 together, you get B2. And so this is B3, so you can decompose into so this, B2, 4 nodes, and this another B2. Okay, also 4 nodes. Okay. So conversely, if we merge 2 BI, then we get a BI plus 1. So that means BI plus BI will give us BI plus 1. Like this. This is a B2, okay, and this is another B2. Together they form a B3. Okay. Now, one can show by mathematical induction that BI has 2 to the I nodes. Okay. And the other property is I choose D of which are left at depth D. Okay. This symbol means I choose D. Okay. So it is written like this. Okay. C and R means the number of ways we choose all objects from n objects. Okay. It can be written like this, n choose r. It is equal to n factorial over n minus r factorial times r factorial. Or sometimes it can be written, expressed in this symbol. And there are some formulas that we'll use later, like this one. Now, we can briefly prove these two properties, the proof of one. Okay, very brief. For the base cases, I equals 0, 1 is obvious. Okay, when I equals 0, the number of nodes is 2 to 0, that is 1. Okay, for I equals 1, for B1, it is 2 to the 1, there's 2 nodes. Okay, 2 nodes. Okay, 1 node. So that's pretty obvious. And then now we assume that this is true for I smaller than or equal to k. Okay, so that means the number of nodes, okay, of bk, okay, is equal to 2 to the k. Okay, so now we consider I equals k plus 1. Okay, and that means we want to find out the number of nodes in bk plus 1. Okay, so n k plus 1, okay, for bk plus 1 is equal to, okay, based on our definition, 1, that's the root, okay, plus the number of nodes of B0, plus the number of nodes of B1, plus the number of nodes of B2, okay, up to bk, right? This is k plus 1. Okay. So based on our hypothesis, okay, nk equals 2k for I smaller than or equal to k. Okay. So we have this, okay, 1 plus 1 plus 2 plus 2 square plus up to 2 to k, and this, okay, the sum of all this is equal to 2k plus 1 minus 1. So that means it is equal to 2k plus 1. Okay. So alternatively, you can prove it like this. Nk plus 1 is equal to nk plus nk, because bk plus 1 is equal to the merging of 2 bk's. Okay, so again, this is equal to 2 times n times nk equals 2 to the k plus 1. Okay. The proof of 2 is also straightforward. Again, we do a brief proof for this using mathematical induction. For the base case, d equals 0, I choose 0 equals 1, so this is true. So for this level, d equals 0, so we are only at 1. Okay. And then again, we assume that it is true for d equals k. Okay, like k d equals 1. Okay. Okay, so we have 3 choose 1. You have this, okay, equals 3. And then now we consider at the depth d equals k plus 1 level deeper. Okay. Now, we discussed before that bi can be decomposed into 2 bi minus 1 trees. So this is equal to this one plus this one. Okay. And one is the child of the other. Okay. Like this. Okay. So this is B3. So you have this B2 and this B2. Okay. So together they become B3. But for this B2, this is the root. Okay. And for this B2, okay, this is the root. So if this is at d equals 1, for this tree, it is at d equals 0. Okay, so that means we have this situation, okay, nk plus 1. Okay, one is at the k level, k plus 1 level, the other is at level k. Okay, one is deeper the other. Okay, as we just discussed. Okay, and then so that based on our hypothesis, so this is equal I minus 1 choose k plus I minus 1 choose k plus 1, and we can make use of the binomial formulas. Okay, and this will give us I choose k plus 1. Okay, but by the way, this is also called binomial coefficients. Okay, so we have made use of this formula. Okay, m minus 1 k minus 1 plus m minus 1 choose k will give us n choose k. Okay. So that means it is also true for the depth k plus 1. That means it is always true. Okay. So we have discussed binomial tree. Okay. A binomial heap is a set of binomial trees where each binomial tree follows min-max heap property, and there can be at most one binomial tree of any degree. Okay. So the heap only allows a binomial tree with a certain degree, only one. Okay. So you cannot have two B1 or two B0 in the same heap. Okay. And it has to satisfy the mean max heap property. For here we just consider mean heap. Okay, so that means the parent has the smaller element. Okay, so for this tree, 5 is smaller than 21, 17 is smaller than 99. Okay, that's the heap property. And for this 12, okay, is smaller than 17.7, smaller than, or equal to, okay, 12, and this is smaller than the children. Okay, so this order doesn't matter at the same level. Okay, whether this is bigger than this or smaller than this, it doesn't matter. But the parent has to be smaller than the children. Okay, that's the property. Okay. So this is a binomial heap, a collection of the binomial trees. So this is B0, okay, B2, and B3. Okay. Now we can link this together using pointers. Okay, so this order 0 can have a pointer pointing to the next higher order binomial tree. There's 5. Okay, and then it has a pointer pointing to the root of all the three binary tree. Binomial tree. Okay. And then we can have another pointer, which is not shown here, pointing to the smallest element, 5 here. Okay. So we can have another pointer so that we can answer this smallest element in constant time because we have pointer pointing to it. Okay. So we can add pointers to join each root to the next in increasing order of the tree order. Okay, starting from maybe B0, okay, from the smallest. And we can also add a pointer pointing to the root of the tree that has the minimum value. Okay. So here's another example, a binomial heap with 30 nodes. Okay. So this B0 points to B2, points to B3. Okay. And then we can make another pointer pointing to this smallest element, that's 8. Okay. Another pointer. And one can use it so that a binomial heap with n items will not have more than log base 2 n seeding function binomial trees. Okay. Now, as you can see, merging two binomial trees satisfying heap properties is pretty simple, and we have to merge the two heaps with the two trees with the same size. Okay. They cannot be of different sizes. Okay. And the time complexity of this operation is big O1, constant time. Okay. Like this example, so we have two binomial trees. Okay. This has a root element 7. This root element 3. So both of these are B2. Okay. And to merge them, what we need to do is to make this 7 to be a child of 3. Okay. So the smaller element will be the root. So we are considering min heaps. Okay. So that means it becomes like this. So you have this B2 merged together. Okay. Then now we have B3. Okay. So the root with a smaller value becomes the new root. Okay. So that's how we merge two binomial trees. And now let's see how we merge two binomial heaps, say H1, H2. Okay. So what we need to do is to merge binomial trees with same degree repeatedly. Okay, remember that a binomial heap is just a collection of binomial trees. Okay. Say if the two binomial trees have bi, okay, so we can merge them together, then we'll get bi plus 1. Okay. And then one of the three may have a bi plus 1. Then we need to continue to merge them to get a higher order binomial tree. Okay. So this is like adding numbers. Okay. So we add these two digits, so 2, we get 2. Okay. It does not generate a carry. Okay. So we deal with the next digits. Okay. 8x to 4. Okay, we get 12. So we get 2 here, but we generate a carry. This carry has to be added to the next 2 digits. So we add this, okay, and then add this. So again, it does not generate carry. Okay, so stop here. And here we deal with these 2 digits. Okay, again, it stop here. Okay. Now to elaborate this more, let's consider an example. Okay. So suppose we have two binomial heaps, H1, H2, H1 has binomial trees B1, B2, B4. So we use this index, the superscript, to denote that it is H1. Okay. And H2 has binomial trees B0, B2, B3. Again, the superscript 2 means it is heap 2. Okay. So the new heap, okay, is obtained by merging H1 and H2. So we have to consider, okay, binomial trees with the same degrees. So first, we start from order 0 binomial trees. So only H2 has B0. Okay, so that we just copy this. Okay. So this is done. So the new tree only has one B0. Okay. And then we go to B1. Only H1 has a B1. Okay, so again, this is done. Okay, so the new tree has a B1. Okay, this asterisk here, a star here, means it's terminal. Okay, we do not need to go further. And then we consider B2. For B2, both trees have B2. So we merge them together. So we get B3. When we get B3, we know that H2 also has B3. So this is not done. This is not terminal. So this B3, okay, has to merge with this B3. Okay, the B3 from the H2. So we get B4. Okay. And then H1 has a B4. So this B4 has to merge with this B4. Okay. And we get B5. So there's no B5 in these two heaps. So this is terminal. So it is done. So our new tree will have B0, B1, B5. Okay. Oh, sorry, our new heap. New heap has the trees B0, B1, B5. Okay. So that's how we merge two heaps. And now let's see, how do we insert a new item X into a binomial heap H? Okay. So to do that, we first put the item X into a new node to form order 0 binomial tree. Suppose we call this B0 dash. Okay. And then itself is a heap. Okay. What we need to do is to merge this B0, okay, dash with any B0 in the original heap, okay, to form, say, B1. Okay. And then if there's a B1 in H, we continue to merge. Okay. So we have to merge BI dash to form BI plus 1 dash until no other BI plus 1 in the heap. Okay, then it's done. Okay. For example, our heap, okay, has a B0, B1, B2, B4, B5. Okay. So when we insert a new item, okay, we create B0 dash. Okay. So X is in B0 dash. So B0 dash has to merge with B0 to get B1 dash. And because H is B1, so B1 has to be merged with B1 dash. So we get B2 dash. And then this B2 dash needs to be merged with B2 to get B3 dash. There's no B3 in H. Okay. So our new heap will have B3 dash, B4, B5. Okay. And then we can adjust our minimum pointer that points to the word that has the minimum element accordingly. We adjust it. Okay. And to delete, okay, the minimum element from the heap is also simple. That means we have to delete, okay, the root from the heap where from the tree that contains the minimum element, and we have a pointer pointing to that node, and then we break up that tree. Then we have to repeatedly merge the remaining binomial trees with same degree to form the new binomial heap. Now let's use the above diagram to see how we delete this minimum element. Okay, this is 5. Okay, so in this heap, 5 is the minimal element. When we delete this, so we decompose this tree to B0 and B1. Okay, so we have this situation. So B0 and B1. So B0 has to merge with this B0. Okay, that has 9. Okay, so we have this situation after the deletion of 5. Okay. So we have this B0, okay, and then this B1. So we will merge this 21 with 9. Okay, then we get this B1. Okay, and we have a B1 here. So this B1 and this B1 have to be merged. Okay, and 9 is smaller, so 9 will be the new root. Okay, and so this is the child of 9. Okay, so we have this B1, so it forms B2. Okay, and there's no B2 in the original tree, so then we're done. Okay, so there's no B2 because this B2 has been decomposed. Okay, so that means our new tree will be this B2, our new heap. Okay, with this B2 with this original B3. Okay, so that's our new heap. Okay, so that's how we delete the minimum element. Okay, and of course we can adjust the pointer, pointing from here to here, and then the minimal pointer will point to 9. Okay, so that's binomial heap. Okay, it's an interesting topic. Okay, so you could study that yourself. Okay. Yeah, thank you for watching.